Okay, hi everyone. So my name is Kylie, and today I'm here with Josh, and we're going to be going over the thermochemistry section of the course. So this is going to cover the important parts of chapter 2 in the workbook. All right, so starting off with 2.1, which covers heat, work, and energy. So here we're going to be looking at a little bit more conceptual stuff as opposed to calculations. And the first thing that you're going to want to understand is the three different types of systems. So we have open, closed, and isolated. So with an open system, you can see matter and heat can go in and out. So in this flask here, maybe some of this water can evaporate, so that's the matter. And then let's say it was cold water and you left it out, eventually would kind of warm up to room temperature, so that's our heat. The same thing would happen with a closed system, so we can have heat moving in and out, but you can see now we have a stopper at the top of the flask, so we can't have that evaporation of the water anymore. So matter cannot go in and out of a closed system. And then with an isolated system, neither matter or heat can go in and out. And so you can see here we have our stopper, and we also have the flask insulated so that its temperature stays more or less the same. Moving on to the next concept you'll want to understand is intensive and extensive properties. So these are easiest to remember if you think of examples. So intensive properties are the ones that are the same regardless of sample size. So temperature makes a lot of sense here because whether you have like a big pot of boiling water or just a little cup, the temperature is the same. It's still 100 degrees Celsius. Extensive properties, on the other hand, are dependent on like how much stuff you have. So mass is our example here because that big pot of water and the little cup are obviously going to register different rate values on a scale. Another important category is state functions. So these are properties that depend only on the final and initial state. So the value of the property is the same regardless of what kind of path was taken to get there. So now that you've gone through the entire thermochemistry unit in class, you might be confused about how this content up here relates to the rest of the stuff that you guys have learned. And so you'll see in the rest of the video that the properties of enthalpy, entropy, free energy, and internal energy are introduced. And so it's important to understand that all of these properties that were introduced to you in this course are extensive properties and they are state functions. And make sure you know this because this is a great thing that can come up in multiple choice questions. Okay, and then throughout the chapter, you're also introduced to the laws of thermodynamics, and there's 3 of them. And so instead of just kind of like listing them all out right now, I'm going to bring them up as they relate to the content because it's definitely more important to understand like their meaning and application more than just like memorizing them. But right now is where the first law comes in, which says that the total energy of an isolated system is conserved. So the significance of this is that it gives us this formula, which basically says that the heat, or Q, that is gained in a given scenario is equal to the heat that is lost, just one is positive, one is negative. And so that's what we mean when we say that the energy is conserved. And then this is the formula for Q, and we'll see how to apply that in the next practice question. All right, so we have a question here, which is 50 grams of ice at 0 degrees Celsius, when placed in water, can cool a maximum of how many milliliters of water from 20 degrees Celsius to 0 degrees Celsius? And then we have some values here. Okay, so let's work through this. First, let's kind of think about it. So we've got, an ice cube, and then we kind of have some cup of water here. And so basically, when they come into contact, the ice is essentially going to cool the water because ice is colder than water. And then it's a little bit backwards to think about, but the water is kind of like warming the ice because it's causing it to melt. So we can set up our formula here of Q gained equals negative Q lost. And so we're going to say that our ice, which is the one that I said was kind of being warmed, is our Q gained, and then our water is going to be our Q lost. And so we actually saw that when that ice is getting warmed and it's getting melted, they already gave us a value for that. So it's going to be 6.01 kilojoules per mole. And then we saw that we had 50 grams of ice. So we're just going to want to also convert that to moles. So we do that by taking our mass and dividing by the molar mass of ice or water, H2O, which is 18. Okay, and then on the other side for the water, you've noticed that we don't have one of these values. So this is where we're going to have to use our Q formula here. So we have negative sign and then MC delta T. And let's actually fill in those values now. So mass of water is what we're trying to calculate. We know that the C of water, the specific heat capacity, is 4.184. And then our change in temperature, so we're going from 20 degrees Celsius to 0 degrees Celsius, so final temperature minus initial temperature will be like that. Okay, so then for this part of the calculation, we just want to make sure we are going to multiply this by 1,000 to convert to joules, just because we see that we have joules on this side. So let's just do that really quickly. So that's going to be okay. So on this side we have 16,694 joules. And then if we just rearrange and solve for M here, so we'll have M equals 16,694 joules divided by 4.184 joules times, and I'm just going to put 20 here, so we can keep it as 20 degrees Celsius. And so these negative, like this will be negative 20, but that will cancel out with this negative sign to give a positive, so that's why I don't have any negatives in my final calculation here. And so as a mass, we get 199.5 grams, and then we know that the density of water is 1 gram per milliliter, so with water, if we have 199.5 grams, we also have 199.5 milliliters. That is pretty close, rounds up to 200, so our answer is D.